Learning Outcome 412. Calculate Fourier transform and inverse Fourier transform pairs using the duality property. This is a method which you can use to create pairs that are very similar to the pairs that you see in Table 4.2 of the book. Pairs between a time signal and a Fourier transform signal. If you look in those tables, you'll see that there are several pairs where they look pretty similar to each other. As for instance, you see a constant in the first column, the time column, and a 2 pi delta of omega in the second column. And if you look further down, you'll see a delta of t in the time column and a constant in the frequency column. That's because of a duality property. And where you find these pairs, you can start by taking one pair of signals, one in time, one in frequency, and you can use duality to calculate the matching pair that goes the other direction. And this can save you a lot of effort if you can find something in a table of transforms that's a little bit less needed today since your calculators can do the analytical integration for you, but there's still quite a few applications for this. Plus, it's a good thing to be aware of. Look at your tables, see what pairs you can find. There's at least 3 pairs in Table 4.2 and at least 1 in Table 4.1. Duality exists because of the forms of the analysis and synthesis equations. They look very similar to each other. They both have integrals negative infinity to infinity. They both have your target signal. They both have an exponential, e to the j omega t, but one's negative, one's positive, and then your dt or d omega. There's a little bit of a difference as a 1 over 2 pi, so we got to make some adjustments for that, plus we got to make adjustments for this negative sign. But because they're so similar, we can make some analyses, and that's where those pairs show up. The way that duality works is we start with our synthesis equation. We're going to replace all of the t's with a negative t. The next step is to replace all the omegas with t and all the t's with omega. So we can see that we've accomplished that with it changing to an omega, changes omega to a t, changes t to an omega to a t, and a d omega to a dt. That's just change of names. Names don't mean anything as to what your variable is. It's like plotting y versus x or x versus t. It doesn't matter what your letters are. The process works the same way. We're going to multiply both sides by 2 pi. That gets rid of the 2 pi on the right side. And using this j inside of our argument is really just a convention. It's not really anything that's an extra variable. So we can put that into our function here. And likewise, we can take it out of our function here. This yields the fact that 2 pi times our time function at minus j omega is equal to the Fourier transform. What we see on the right here is our Fourier transform function, our analysis equation. And that's going to yield 2 pi times our time signal with a minus omega and the Fourier transform of our x of t signal on the right side, which is going to be an x of j omega, but with a letter t in there. So in general, look at what your x of t signal is and call it some function g. G stands for the form of the equation. Is it an exponential? Is it a sinusoid? Is it a constant? Is it linear? And we know that that x of t is going to have a pair that's going to be an x of j omega. And that's going to have some functional form also. We're going to call that functional form f. Then we know that the opposite pair, we're going to call it y, which has a transform of y of j omega, is going to have that same functional form that we had in our first pair, but instead of having an omega, it's going to have a t. And then the transform of that is going to be the same functional form that we had for our original time signal, multiplied by a 2 pi. The t's get replaced by minus omega. And this lets you develop new transform pairs. Let's try an example. If we take the transform pair x of t is 1, which transforms to x of j omega equals 2 pi delta of omega. This is from table 4.2, property number 5. Our functional form of our time signal, called g of t, is just 1. The functional form of our transform signal is called f, and that's 2 pi of delta of omega. If we take f of omega and replace all the omegas with t, we get 2 pi delta of t. If we replace our g of t with g of minus omega, There's no omegas in here to make a substitution in, so you have to just kind of think this is a special case. And then multiply it by 2 pi. That gives us 2 pi times 1, which is just 2 pi. That means that the transform of 2 pi delta of t is 2 pi in the frequency domain. Or if we divide 2 pi from both sides because of linearity, we get delta of t as a transform value of 1. And this you see in table 4.2 is property number 10. Those are duality pairs, and this is the procedure that you use to get that second transform. Work through there, figure out what the G is, figure out what the F is, make sure you understand this. Let's try another example. This is transform pair number 10 from table 4.2. We have a single time-limited pulse that's going to transform to a sinc function. Note this is not a periodic pulse train. Our g of t is just the functional form of our time signal. Our f of omega is the functional form of our transform. Therefore, f of t is going to be our f of omega, and everywhere there is an omega, replace it with a t. The other side of the transform will be 2 pi g of minus omega. Take our g function, everywhere we see a t, replace it with a minus omega, and scale it by 2 pi. This capital T is just a constant, so instead of calling it t, let's call it w, not omega, w. So where there was a t, there's a w, where there was a t, there are w's. And then by linearity, we can divide both sides by 2 pi. The 2 pi shows up here with our sinc function, wind up with our g of minus omega by itself, and no 2 pi scale factor over here. And this is table 4.2 property number 9. Another example of a duality pair and the use of duality to derive a new one. This may not be very helpful because you already have table 4.2 property number 9 in your table, but had this not been there, you could have used duality to create it.